Different properties can be set for each type of source, but we'll first cover the settings which are common to many of the sources before going into detail about individual source types. All sources can be added from the Sources menu in the main toolbar at the top of the window. In the Sources menu, you'll also find the Global Properties option at the bottom of the list. This opens up the Global Source Options window where you can set the default frequency wavelength settings or time domain pulse settings which are used whenever you add a new source. Let's consider a Gaussian beam source. This can be added from the Sources drop-down menu. Click on the Edit button, or use the E keyboard shortcut to open the Source Edit window. In the General tab, some of the settings here that are common to most of the sources are the amplitude and phase. The amplitude sets the maximum electric field amplitude of the source, and the amplitude is important when simulating non-linear materials. It's not as important for linear systems, since the default amplitude of 1 volt per meter can be used to run the simulation, and the results from monitors can then be scaled as a post-processing step to get the results for any desired source spectrum. The phase setting sets the phase of the electric field at the center of the source injection plane. This is usually used if you have multiple sources and you want to impose a relative phase difference between the sources. Under the Direction and Polarization box, the Injection Axis setting sets the main propagation axis. This can be set to X, Y, or Z axis. The direction can be set to forward or backward. And this determines whether the source is injected towards the positive or negative axis direction. The angle, theta, and phi settings can be used to rotate the source propagation direction, where theta is the angle from the injection axis, and phi is a rotation applied in a right-hand context around the injection axis. The polarization angle setting sets the direction of electric field polarization. After setting up the source direction and polarization, I can check the CAD viewports to verify the injection direction, indicated by the pink arrow of the source, and the polarization direction of the electric fields, indicated by the blue arrow. Under the Geometry tab, we can set the position and spans of the source. Depending on the injection direction and type of source, some of the span settings may be disabled. In the Frequency Wavelength tab, this is where you can either set the frequency or wavelength range of the source, or time domain settings of the source pulse. These settings will override the global source settings. When simulating linear systems, it's sufficient to use the Set Frequency Wavelength option and specify the start and stop wavelength range of the source to use the automatically generated source pulse, rather than using the Set Time Domain option to set the properties of the time domain pulse. This is because the CW normalization will normalize away the spectrum of the pulse to give the result as though a uniform spectrum is injected. For more information, see the CW normalization link below. On the right side of the panel, you can see the spectrum of the source pulse as well as a plot of the time signal of the pulse. You can zoom into the plots by selecting a region of the plot with your mouse cursor. Now that we've seen how to set up the basic properties of sources, here are some useful tips to know when you set up a source. The source has a finite 2 to 3 cell wide injection region, which is displayed as a gray shaded region in the CAD view. To avoid any injection errors or scattering at the source injection plane, the shaded injection region should always be contained in one medium, meaning that the source injection region shouldn't intersect with two different objects. However, this constraint does not apply when using the mode source to inject the mode of waveguide or fiber, since the mode profile injected by the source is calculated for the given cross-section of the structure that the source intersects, so there won't be any scattering when injecting this field profile. In the Geometry tab of the source, the span settings are enabled based on the source injection direction for the plane wave, Gaussian beam, and mode sources, so be sure to set up the direction first before setting up the geometry. For example, if you have a plane wave source propagating in the x direction, the x span of the source is not relevant, and the setting will be grayed out in the edit window. Under the Frequency Wavelength tab, you can use the plot of the signal versus time to make sure that the simulation time setting of the FDTD simulation is long enough to include the entire time signal of the source pulse. This can be important when injecting at frequencies below the optical range where a longer source pulse is generated. It's also important to know that the simulation mesh size will adapt based on the source wavelength. Smaller wavelengths result in a finer mesh, and you can see that for a source wavelength of 0.5 microns, a finer mesh is generated compared to using a source wavelength of 1 micron. Therefore, it's best to look at the simulation mesh after setting up the source. A final tip is that the fields inside the source injection region may be unphysical, so when setting up monitors to record the field results, make sure to place the monitors outside of the gray shaded source injection region. Or, if using a monitor to record the field profile where the monitor intersects with the source injection plane, be aware that the fields measured in the two cells around the source injection plane may be unphysical. In the Knowledge-Based Sources chapter, under the Sources Advanced Techniques subsection, you'll find additional advanced information such as tips for adjusting the source bandwidth, simulating frequencies below the optical range, simulating coherence, and more. In the following units, we'll cover each source in detail.